So we're saying, given the following information, there's a reaction. We've got its equilibrium constant. That's a more realistic equilibrium constant because it's either a really big number or in this case it's a small number. And then we've got a second reaction there. We've also got its equilibrium constant. Then it says determine the value of the equilibrium constant, Kc, for the reaction shown below here. 2HF plus C2O42 minus yields 2F minus plus H2C2O4. Okay, so once again, the top two equations, these are like our menu. These are what we get to choose from. And we're going to use those to try to build, this is the one on the bottom, I call this the target reaction. This is what we want the top two items from the menu to end up looking like. So it's kind of like a puzzle. We got to put the pieces of the menu together so they look like the target reaction there. First thing I need from a target reaction, I need two HFs. All right, am I going to get an HF from reaction 1, or would I get an HF from reaction 2, Maddie?
1.
Yeah, from the first reaction there. However, I want two HFs, not just one. So I need to take everything from reaction 1, and I need to double it. I'll rewrite it neater down on the bottom in a second. I'll double everything. If I double everything, what do I have to do to my equilibrium constant? What do you think, Piper?
Double it as well.
That's what I would do if it were a delta H, okay? So I like the way you're thinking. If it were a delta H, I would double it as well. But with equilibrium constants, we kick everything up a notch. So instead of doubling it, I need to square it. We kick it up a notch for equilibrium constants. So now I'm going to rewrite that equation. I'm going to say 2HF this time. Yields 2H plus 2F minus. And then for Kc, I don't know why I put an equal sign there. For Kc, I'm going to take that number, 6.8 times 10 to the negative fourth, and I'm going to square it. I'll pass out some calculators too. Let me get this number first. And I'm getting, I'll keep one extra sig fig as I work through, so I'll call it 4.62 times 10 to the negative seventh. All right, so we doubled everything in the reaction because we wanted two HFs. Therefore, we had to square the equilibrium constant. Okay, next thing on the menu, actually next thing in the target, is C2O42 minus. Which reaction can I find some C2O42 minus in? Joseph? The second one, but it's in the wrong place. So Sydney, what do I need to do to that reaction? I need to flip it. If I flip the reaction, what do I have to do to the equilibrium constant? Shelby? If you've got yesterday's notes out, go to, I don't remember if it was rule 1 or rule 2. I think it was rule 2 from yesterday. Reciprocal. And I lost my TV. That means 1 divided by. So what I want you to do, everybody, you can divide 1 divided by parentheses 3.8 times 10 to the negative 6. So I'm going to do 1 divided by all of that stuff. And then I'll write my equation flipped, 2h plus again, some people don't have to rewrite everything. They can do it in their head, but not me. I have to write it down or I'll get lost. And then H2C2O4. All right, so my new equilibrium constant is going to be over. Let's see. Carter, what did you get for your new equilibrium constant after you divided that? 263,157. Good, that's what I got too. And so I'm going to go with 3 sig figs there just so I have a safety digit. So I'll just call that 263,000. Switch to, there we go, 263,000 for my equilibrium constant there. Then I need to make sure that I did that right, so I'm going to add up these 2 reactions and let things cancel. MK, what's something that might cancel as we look at these 2 equations? Yeah, good. The 2H pluses are going to cancel for us. One's on the left side of the arrow, one's on the right side of the arrow. And I think that's all that cancels. So now we drop everything down, get our final reaction, and we just make sure it looks just like the target reaction was supposed to look. 2HF plus C2O4 yields H2C2O4 plus 2 fluorides. All right, and then the whole point was to get my final equilibrium constant. I'll write it down below because I'm out of room. I'll say Kc equals, and it's going to be the product. So 4.62 times 10 to the negative 7th times 263,000. I'm getting about 0.121. I can round that to 0.12 because I just had the 2 sig figs in the first place. And I got an equilibrium constant for an unknown reaction, which I call the target reaction, from 2 reactions that I was able to add the reactions together, but instead of adding the equilibrium constants, I multiplied them. If those had been delta H's, from way back when, we would have added them together. But with equilibrium constants, you kick everything up a notch. Anybody have any questions about that? Yeah.
So if there were like a 3 coefficient, would you just cube it or something?
Yeah, so if you ever had to triple a reaction, you would cube, raise it to the 3rd power, your equilibrium constant. Exactly. All right, so that's dealing with that. The next couple of things we're going to deal with today are how we can use equilibrium constants when we're not necessarily at equilibrium yet. And the first way we're going to deal with that is something called the reaction quotient Q. That's what the bell ringer was about. Q is basically the same exact, it is the same expression as K. It's products to the power divided by all the reactants to the power, where the power is what was the coefficient. The thing is, we just call it Q if we want to indicate the fact that we don't know for sure we're at equilibrium yet. Usually it might be the initial reactants, but it could also just be a mixture and you don't know if it's at equilibrium yet. Maybe it's reacted for a minute. But one way to decide if it's at equilibrium yet is to calculate it, but you just call it Q, and then you compare it to the known value of K. And this is all going to end up being about, is your value greater than the expected value for K, less than the expected value for K, or is it exactly equal to K, in which case you're already at equilibrium. So it's the same idea as K. All right, so first one, this is kind of the answer to that bell ringer. Yeah. Yeah. And the reason it's a Q is just because it's at least this is one letter. You can explain why it's the letter it is. It's a quotient. Quotient is where you divide, and these are all about ratios. So you're dividing to get those ratios. All right. So first statement was the answer to the bell ringer. If you solve for Q and you get the same thing that K was supposed to be in the first place, then that reaction is already at equilibrium. That makes sense. All right, our next possibility is going to be if Q is greater than K. Think about what the expression K or Q, what it's supposed to be all about, is the products over reactance ratio. So when it gets to K, you've got just the right ratio of products to reactants for that reaction. If you solve and Q is too big, that means your ratio has too big of a numerator or the denominator is too small because Q is too big. In that case, you've got too much products already. So to fix that, the reaction is going to kind of go backwards and get rid of some of those products and make more reactants in the end. So when Q is greater than K, the reaction goes backwards. So the reaction will proceed, sometimes we say to the left or backwards if Q is greater than K. Because it needs to get rid of some products and make more reactants until that ratio gets to where it's supposed to be. All right, and then the opposite, if Q is less than K, that means your ratio is too small. You don't have enough products yet, or you have too many reactants because the ratio is too small. And to fix that, the reaction needs to go forward so that it can make more products up top for a bigger numerator, get rid of some of those reactants out of the denominator until the ratio increases to the point, until eventually, if you let the reaction keep going, Q will eventually get to K. That's kind of the point. It's just called Q when you're on your way to equilibrium. The reaction is going to keep going and proceeding until Q will eventually equal K if you just let it sit there long enough. So it's all about that ratio. But if I'm, taking a test and I'm in a hurry or something, I like a quick way to remember things. That's one of those backwards things to remember. We always typically we think of it Q first, because you're solving for Q, you're going to compare it to K. I just think of the arrows pointing like the opposite direction from the greater than and the less than sign. So if Q is greater than K, I know, okay, I need to point my arrow the other way. The reaction is going to proceed backwards and make more reactants. If Q is less than K, the reaction needs to proceed forward in the other way. So just kind of a way to remember it is just the backwards direction of that greater than or less than sign. So this one I had to squish onto that page to get it to fit just right here. It says at 1,000 Kelvin, once again, they're just telling us the temperature because they like to give us a temperature since the equilibrium constant kind of depends on the temperature. The value of Kp for the reaction is 2SO3 yields 2SO2 plus O2 gas. That value, when it's K itself at equilibrium, it should be 0.338. Now, we want to calculate the value for Q and then predict the direction the reaction will proceed toward equilibrium if the initial partial pressures are 0.16, 0.41, and 2.5. The first step in all of these is to write the expression, the equilibrium constant expression in general. So that's with the letters, no numbers yet. So I want to find what we call it Kp, so we'll use partial pressure, so we use the correct format. All right, so I'm going to say partial pressure. What partial pressure should go up on top in terms of SO3, SO2, or O2? MK, what's going to go on top here? You got it. Good job. SO2. Am I going to do anything to that SO2 partial pressure? Good job. I'm going to square it because of that coefficient right there. Times, you said O2 as well, so the partial pressure of oxygen. And then, Claire, what's going to go on the bottom of this expression? Good job. Partial pressure of SO3 raised to the second power because it's got a coefficient of 2 in front of it from the reaction. If it's at equilibrium, that ratio is supposed to be 0.338. By calling it Q, we're just saying, I'm not 100% sure it's at equilibrium yet. Let's just try the numbers they gave us. So in place of SO3, oh, thank you for telling me. I'm not sure. Like this. You should play a game and see how long I'll keep going. You don't tell me.
We can take bets.
No, really, I appreciate it. Yeah, take bets. 45 minutes.
45 minutes. You get $1 per minute.
On my iPad, it just everything looks normal. There we go. Okay. Let's put these numbers in now. So 0.16. Will 0.16 go upstairs or downstairs? Vivi? Downstairs, yeah. So I'll say 0.16 squared. Again, I love this. I don't have to worry about units in terms of these equilibrium constants once I get started with it. SO2, 0.41. Alice, where should I put 0.41? At the top, yeah. And that leaves oxygen to be right here, 2.5. All right, so I'll just do this. Make sure your calculator knows what's supposed to be upstairs and what's supposed to be downstairs. So when I square that 0.16, I'm going to put that in parentheses on the bottom, just so my calculator knows for sure all that's downstairs. And I'm getting 16.4. All right, now, they told us in the top, K is supposed to be 0.338. But right now, Q is 16.4. So I can tell Q is greater than K, right? Q's too big. That means I've got a top-heavy ratio. This ratio needs to be reduced by a lot. In order to reduce it, that would mean I would need to decrease the amount of SO2 and the amount of O2. In order to do that, that means the reaction needs to proceed to the left. I'm just going to write that. The reaction will proceed to the left, or you can say toward reactants. Toward making more reactants. It's also called toward the, well, if somebody says toward the left, that means toward more reactants. It needs to make more SO2 and, it needs to make more SO3. This reaction needs to make more SO3. All right, so that's what Q is all about. The math for it's easy. If you can do K, you can do Q. And then you just compare your answer if it's greater than, less than, or basically equal to. All right, any questions so far? All right, so what we're doing, again, we're using the equilibrium constant and comparing it to things that aren't necessarily at equilibrium. And that's what I want us to take a look at for the last little bit of class is other times where you're not at equilibrium yet, but you're on your way there. So here's another equilibrium problem. Got an equilibrium reaction there. It says a closed system, so that means it's sealed off. You're not letting anything in or out. It's got a concentration of 1 molar H2, 2 molar of I2, and we've got a temperature there. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 molar. Calculate the equilibrium constant, 0.448, for the reaction taking place, and then they even give us a balanced reaction here. All right, so I'm going to write down some of the numbers, and then I'll switch to a new slide so I've got the room to write underneath it. Some of the stuff they're telling us initially I'm probably not in equilibrium yet. So some initial amounts that I can deal with is H2 is 1 molar, and I2 is 2 molar. Then, once I hit equilibrium, they're telling me the HI concentration. Only one of these numbers is allowed to go in an actual equilibrium constant expression, and that would be the 1.87 molar of HI. I'm not allowed to use these two numbers in the true equilibrium constant expression because I'm not in equilibrium yet. I also know the equilibrium constant, K. Kc, they're telling me is, oh no, I'm going to calculate it. All right, well, I want you to leave a little bit of space underneath your reaction because we're going to use the space underneath there to solve something. Oh, it's on there again too. But let's just go ahead to the right-hand side of the reaction. Let's go ahead and write the equilibrium constant expression. What's the expression we're looking at here? So you give that a try. First, you write the equilibrium constant expression, and then I'll get somebody to tell me what they wrote down. Just the expression, the number, no numbers yet, just letters where you're maybe squaring stuff, but no actual values from the story problem. Okay, Kira, what's your expression?
Kc equals the concentration of HI squared over the concentration of H2 and the concentration of I2.
You got it. Good job. All right, we've got an expression. The expression looks good there. Again, my point is, the only number that I'm for sure allowed to plug into that expression, because I want to solve this for Kc. I can put the 1.87 on top and I can square it, but I don't know what to put on the bottom yet. To figure out what to put on the bottom, when you're dealing with a mix of initial concentrations and final or equilibrium concentrations, you got to stop and you got to make a little table under the chemical reaction that looks a lot like something we've seen before. Don't put these letters down yet, but we're going to solve this in the very same way. So remember these BCA tables that we used before. We're not going to call it BCA anymore. It's got some new names for it. Instead of before, we're going to use I for initial. We're still going to have C for change. Sometimes you'll see a delta symbol. If you look up some example problems or something, they might use the delta to represent change. And then instead of after, because it's reaching equilibrium, because you do this with equilibrium problems, we put an E. So we call these ICE tables instead of BCA tables. So we're going to make an ICE table underneath. And we're going to treat it the same way we treated a BCA table. So it's great that you know how to do those already. The thing that I really like about these ice tables is these ice tables almost always have really simple coefficients. Like this is a 1, a 1, and a 2. They rarely have like a 5 and a 4 or something for their coefficient. So it's really easy to deal with the numbers on these ice tables most of the time. All right, now we can use the ice table to get our equilibrium amounts. The numbers that we get down here, these are the ones that we're going to be allowed to put into the expression and solve for capital K, equilibrium constant. So we start off with our initial stuff. The initial amount of H2 was 1 molar. Also, these use molarities. You know, we use moles a lot for the BCA tables. These most frequently are going to use molarity. And I2, I'm going to put 2.0 molar in for I2 because that's what they told me in the story problem I initially had. Before the reaction started, they didn't mention anything about HI. Most of the time you'll have a 0 there, just like you did with BCA tables. But you won't, every once in a while, you might actually end up putting a product there initially. If they tell you there was initially 5 molar of HI, you can put that in there. So with equilibrium, sometimes you start with some of the products already there. Then, I know one more piece of information from this problem. What's one more piece of information that I know from the story problem? Will Broadfoot? One more number from the story problem.
Concentration of HI.
You got it. When is that concentration of HI? Is that the initial, the change, or the equilibrium concentration? It's not it actually will be the change, but the way it's stated in the problem, it's the equilibrium concentration. It will be the same number there, but the reason is because they're stating it as a 1.87 at the equilibrium concentration. Since you started with 0, the change is 1.87. Now the change row is where you get to use those coefficients and relationships there. So this is what we've done before. We divide by 2, multiply times 1, and then the same thing there. Anything that has a 1 in front of it needs to be half of 1.87. All right, what's half of 1.87? Ainsley? Or 1.87 divided by 2. You got it, 0.935. These are reactants, so just like you're used to, you're going to subtract the reactants. And in that way, I'm going to be able to figure out what these equilibrium concentrations are. You just tally up the rows, 1 minus 0.935, 0.065. And it's going to be 1.065, I think. These are still molar concentrations here. All right, and I did all that work because now I know the equilibrium concentrations of all of this stuff. And I can solve for the equilibrium constant. I'm going to say, what goes on top? And now I'm ready to solve for my equilibrium constant because I've got all these equilibrium values. Mackenzie, what should go on top of this ratio in terms of numbers?
Are you looking at the change row?
Good question. We're going to use the equilibrium row because it's a great question, because we're solving for the equilibrium constant. And we're calling it capital K. We're not calling it Q. We're calling it capital K. It's the real equilibrium constant. You have to use equilibrium values. Good. 1.87 squared goes up on top. What's going to go on the bottom, Davis?
I put 0.065 times 1.065.
You got it. Good job. All right. Now let's just do the math again. If you put a bunch of stuff in your calculator at one time, make sure it knows what order everything goes in and what's on top and what's on the bottom. So you might want to use an extra set of parentheses for your downstairs. Okay, you good at calculation there. Adam, have you done it yet? Yeah, punch it in for me.
I got 27.
Give it another, or I'll get somebody. You might have typed in something a little bit off there. Did you square the top maybe?
No, my bad. Okay, 50.7, is that better?
That's it. About 50.5 or so. You got it. Good job. So I'll just round it with 2 sig figs. I could round it to 51. 50.5 would be fine. But that's what we're going to get for that one. If you did that one too fast and you just said, oh, okay, I can do equilibrium, and I'll just put the 1 and the 2 in and the 1.87 squared, you'll get the wrong answer there. You have to use the concept of equilibrium, and to do that, you're going to use an ice chart. All right, so any questions about using the ice chart in that problem? Yeah.
Okay, so if it's 51, what's that? Does that mean it's making products? Or?
So that means most likely this reaction is more likely to be product favored in the end. We're more likely to have more products in the mixture than reactants in the mixture. When it's 50 or more, we're getting to the point where we can pretty much go with our gut and go with that assumption. Sometimes when you square things or you have more reactants than products, that can mess things up a little bit. So we said K needs to be much, much greater than 1 to be 100% sure of it. So if it's like the K is 1 times 10 to the 4th power or something, you know for sure that's definitely much greater than 1 and it's product favored. These can go kind of sway either way, but this one, it's up to the point where I can be pretty confident that this one's more product favored. Yeah. All right, let's save the last question for tomorrow because we're going to tomorrow we're doing ice charts tomorrow. Today's assignment focuses more on the first 2 things we did, flipping reactions, doubling reactions, and solving for like